Hello, everyone, and welcome to a bonus question due to me not wanting to spend most of a class period on one problem here. This is a little bit lengthy, and uh, and a lot of details involved, so I didn't do it in class. But I'm going to do it here just so that you can see how it looks. So first things first, we need to think about our domain here because most of the other examples, it's been all real numbers, but in this case, we actually do have some restrictions because remember the square root can't be negative. So that means that we have to keep this either positive or 0. It can be 0. So we're going to include the values. And as long as when I square this, this doesn't get larger than 8. So square root of 8 is as big as we can get on either side. So square root of 8 or 2 root 2. So from negative 2 root 2 to positive 2 root 2. So for example, we can plug in 0. That's fine. Right, because then we get the positive 8. But then if we plug in like 3 squared is 9, 8 minus 9 is negative 1. So negative 2 root 2 to positive 2 root 2. So that's going to affect how our sign charts look when we get there. But let's take this first derivative here. First derivative has a couple different things going on. This is going to be a product rule nestled with chain rule nestled inside of it. So go ahead and try and do that first derivative. And if you need to see the details of it, then keep watching. Otherwise, I'll put a timestamp where you can skip and go to all this stuff over here. For those of you that need to see that first derivative, this is a product rule, so this is first. Times derivative of the second. Derivative of square root of 8 minus x squared is going to be 1 over 2 square root of 8 minus x squared. So in other words, this is 8 minus x squared to the 1/2. So it's going to be 1/2 times the thing to the negative 1/2. That's why it goes on the bottom, and that's why it's still a square root. But then, of course, on top of that, you need the chain rule. Times derivative of the inside part. This is a negative x squared, so that's going to be a negative 2x. Plus our second, which is square root of 8 minus x squared, times derivative of the first. Derivative of x is 1. And so now here comes the tricky part. Because in order to figure out where this is 0, it's going to be much easier to get a common denominator here. So in order to get a common denominator, I'm actually going to have it match the thing on the bottom here. So on this piece, I'm going to multiply top and bottom by what's on the bottom here. So what did I get a common denominator? Square root of 8 minus x squared. So that, sorry, this is y prime. So that when I get the final answer for that first derivative, it's all going to be under one fraction. So we're all over 2 times the square root of 8 minus x squared. Well, here we have an x times a negative 2x. That's going to be negative 2x to the second. And then we have plus, this is also over 2 times the square root of 8 minus x squared. That was our goal. And then this is, we've got a 2 here. And then this is square root of 8 minus x squared times square root of 8 minus x squared is just 8 minus x squared. So if we put it all under one fraction, then this is going to be 2 times 8 is 16. And then we have a negative 2x squared. Well, that's going to be negative 2x squared minus a 2x squared here is going to be a minus 4x squared. And if we want to, we can factor the 4 out here. I'd say we should do that because it's going to be easier to see what points we're interested in here. Over 2 times the square root of 8 minus x squared. And if it makes you feel better, you can cancel this 2 with this 4 and say, here's a 2, here's a 1. If you wanted to do that earlier, it would have been done here. And that would have caused the same effect. But here's the key part. Welcome back, those of you who have this first derivative. We got common denominator, wrote it all as one big fraction. Because that's going to make it much easier to be able to tell where this first derivative is 0. Where it's undefined is at the endpoints. So this bottom is 0 at my negative 2 root 2 and positive 2 root 2. So those are candidates. So critical points are x equals plus or minus 2 root 2. And we should always check the endpoints whenever we have endpoints. But then we also have plus or minus 2. And that's within our interval. Because this is square root of 8 and this is square root of 4. And so our sign chart here for the first derivative should look like this. We have negative 2, we have positive 2, and then we have our endpoints. And so we're going to need to get each interval and figure out what we have here. So let's see. Between negative 2 root 2 and positive 2 root 2, I'm going to go ahead and use this form of it. And we'll say the bottom's always going to be positive because it has to be. If it's not positive, then it doesn't exist. So this top is all that matters. So really, we're interested in the 4 minus x squared piece. 4 minus x squared, let's see. If I put in, for example, negative square root of 8 and negative square root of 4. So let's do negative square root of 5. So if I put in negative square root of 5 and square it, well, then it's going to be, it's going to be a positive 5. Negative times negative is positive. Square root of 5 squared is 5. 4 minus 5, negative. Something between negative 2 and 2, that's much easier. Let's plug in 0. That's going to be positive. And then same idea here. Square root of 5 is in between here. And if I put square root of 5 and square it, 4 minus 5, negative. The other idea is once we hit to the right of 2, this number is going to be overpower the 4 and make the number negative in general. And so that gives us our increasing and decreasing intervals. So that is going to be, we're increasing from negative 2 to 2. And then we're decreasing everywhere else in the domain. So in the other two zones here. Union with 2 to 2 root 2. Then we want to know which ones are max and which ones are min. See if you can take a few seconds to pause and piece out, including the endpoints, where do we think max and min is going to be? And hopefully you have decided that we start at a lower point or at a point and then start going down. So that means that negative 2 root 2 is going to be a maximum. And then we're going to hit, we're going to decrease all the way to negative 2. And then we're going to start going up again. So negative 2 is a minimum. Then we go up and we go up until we hit 2. That's a maximum. And 2 root 2, we go back down and hit that point, so that is a minimum. Well, if I plug in positive or negative 2 root 2, these are going to be zeros. 0 and 0. And then if I plug in a positive or negative 2, then let's see, 8 minus 2 squared, that's 4. 8 minus 4 is 4, so square root of 4 is 2. Times 2, so this one is 4. And then this one's going to be the same thing, except out here is going to be a negative 2, so this one's going to be a negative 4. So this one is absolute. This one is absolute. And the endpoints are going to be relative minimum, relative maximum. But we should test the endpoints. It's a good example of testing the endpoints to see which one is the largest value. So that's everything with the first derivative. Now let's move on to the second derivative. So I'm going to go ahead and write that out so that we can do that. And again, if you want to work ahead and try and get that second derivative, I'll give you a point to skip and think about what we're going to end up with is a fraction and a fraction. So again, you'll want to multiply on top and bottom, and this time you'll want to get rid of the fraction. Low d high, derivative of 8 minus x squared, 2x squared, that's going to be a negative 4x, minus high d low. We already did d low. We already talked about how it's a chain rule going inside of the square root. And so I'll just go ahead and say that derivative is negative x. If I cancel the 2's this time, negative x over the square root of 8 minus x squared. Over the square of what's below. Now, our goal in this next step is that I don't like this fraction nestled here inside of another fraction. So I want to cancel that out. And so the way to do that, to cancel out the square root of 8 minus x squared on the bottom, is to put one on the top. And remember, to simplify this, keep it the same, you got to do the same thing on top and bottom. And so that's what we're doing here. And our overall goal is this canceling that's going to happen over here. But we have to multiply out the rest of it. So if it's multiplied over into this piece, I've got a square root of 8 minus x squared times the square root of 8 minus x squared is just 8 minus x squared. Times the still times the negative 4x. Minus, and then when I bring it over to this piece, here's the good news, times, well, I have this canceling here. And so I just have negative x. And then on the bottom, I'm bringing another square root of 8 minus x squared along with me here. So now there's 3 of them cubed. And so let's get some distributing and simplifying happening over here. I've got 8 times a negative 4x. That's going to be a negative 32x. And then a negative x squared times a negative 4x is going to be positive 4x cubed. Minus, I've got an 8 times negative x is a negative 8x. And then I have a negative 2x squared times a negative x is going to be a positive 2x cubed. And that's still all over 8 minus x squared quantity cubed. So let's see. That's going to be my x cubed terms. I've got a 4x cubed minus a positive 2x cubed. So that's going to be positive 2x cubed. And then I'm going to have minus, that's a negative 32x minus a negative 8x is going to be a minus 24x. So this is my most simplified form of the second derivative. So now we want to look at where this is 0 or doesn't exist. Well, it doesn't exist at the endpoints again, but we're not interested in that for these things, for inflection points. And so that leaves where the top is 0. So when does 2x cubed minus 24x equals 0? Well, we can take out a 2x, and we're left with x squared minus 12. So we get x equals 0 here. And then x equals plus or minus square root of 12. Or plus or minus 2 square root of 3. If you want to simplify that down. But guess what? Remember, this was square root of 8. And so these things are out over here, not in the domain. We don't care about it. If I plug square root of 12 in here, I'm going to get an undefined value. So we don't care about that. We do care about 0. So we're going to make our sign chart out here. And good news is that the sign chart's a little bit simpler, because the only value that we care about is 0. So let's think about, if we plug in a positive value, this thing's always going to be positive. Sorry. Say that again. If we plug in a positive value here, well, the bottom's always going to be positive. And so I'm just interested in the top. Well, let's see. X squared minus 12. No matter what, x squared minus 12 is going to be negative. And so I'm just interested in the 2x. So when I plug in a positive number, I have a positive times a negative is a negative. And then when I plug in a negative, I have a negative times a negative is a positive. So that means we're concave up from negative 2 root 2 to 0. We're concave down from 0 to 2 root 2. And our inflection point is at 0. Plug in 0, I get out 0. So just to remind you, the only things that are points are inflection points, maxes, and mins. Those are points. Those are specific locations on the graphs. These, remember, are intervals. Because of the parentheses, they may look like points, but they're actually intervals. So just keep that in mind when you're looking at these. So just to recap, this helps us give us a flex our derivative taking muscles, because there's a lot of pieces going on in here. So I think this problem is valuable for that reason. And I think that it helps us put a lot of pieces together and keep and start to see when we might simplify and when it's valuable to simplify. Because if I gave you this form of the derivative and asked you, okay, when is it 0? Not as obvious as it is down here. And so when you get asked about when should I simplify, a lot of times it is, what is it useful to simplify to? So you'll notice there are some times when I didn't cancel as much, and that's because it wasn't important to cancel. You'll notice that I didn't really touch the denominator because I didn't care about the denominator. I already knew when it was 0. I was just interested in simplifying the top so that I could figure out when it was 0 easier. So simplifying when it's useful. All right, thanks for sticking around and watching it. Seeing this bonus problem, hopefully that helped you get some more confidence on a more complicated problem. And I will talk to you more next time.